Let's look at some more examples regarding the tree diagram. Alright, so now we want to refer to this special kind of dice. Alright, now for this dice you have colors. Number 1 and number 4, they are colored red. The other 2, 3, 5 and 6, they are colored black. So in other words, if the die is fair, then you can have 1/3 probability to have a red, 2/3 probability to be black result. Alright, never mind the number, we just look at the color. So now we roll 3 dice. Alright, this kind of die, we roll 3 of them. How likely is it to have exactly 2 of them red color? Exactly 2 of them, they are red color. Alright, so let me show you 2 mistakes. Alright, one of the most common mistake is that people think exactly 2 red color, so each red color for the first die is 1/3. Alright, the other red color will be 1/3, so the answer goes to 1/9. Alright, 2 red color, that's what you said, right? So 2 red color, we have a red and a red, so that goes to 1/9. Alright, in other words, let me illustrate the thinking. She thinks that the answer is the probability of having red and red. So the red is 1/3, the other red is also 1/3. So the answer goes to 1/9. Alright? No, that's wrong. Alright, that's wrong. I will tell you why. Alright? But let me show you the second mistake. Alright? In the second mistake, she realized that if one of them is red, the other is red, because you want exactly 2 red, so the third one cannot be red. The third die must be black, alright, in order to have exactly 2 red. So the answer goes to 1/3 for the red, 1/3 for the red, and 2/3 for the black. So the answer goes to 2 out of 27. This is going to be the right answer. But no, unfortunately, the second way is also wrong. Alright, so let me show you the correct way. The correct way should be, well, it is true to have 2 red and 1 blue. 2 red and 1 black. Alright, there's no problem about that. But to do that, there are actually 3 ways. You can have the first 2 to be red, the last one to be black, or it may be the first and the third one, they are red, but the middle one is black. Or it can be like the first one is black, but the last 2, they are red. Alright, in other words, these 3 terms, if you pay attention, these 3, they are the same. So that would be 3 times this one, 3 times 1/3, 1/3 and 2/3. Alright, so that would be 3 times that number, and the answer goes to 2 out of 9. This is the correct answer. Alright, because this 2 red and 1 black branch is going to repeat itself 3 times. Alright, it can be like this, it can be like this, or it can be like this. Alright, now it is confusing because I did not draw the tree diagram. Alright, if I draw the complete tree diagram, you realize that only the third method is correct. The first 2 methods, unfortunately, they are wrong. Alright, only the third method is correct. Alright, do not make this mistake. It's very common mistake. Alright, in the first two methods, they are all wrong. Exactly 2 red, you just multiply 2 red without looking for the third one. It's wrong. Alright, because to have exactly 2 red, the third one must be black. Alright, not just that, because the 2 red and 1 black actually repeats itself 3 times. Now that would be obvious if you look at the tree diagram. Alright, imagine that is die number 1. Alright, it can be red, it can be black. Alright, and then you have die number 2. Die number 2, once again, it can be red, it can be black. And then we have the final die number 3. Right, because I did not draw the tree diagram in my first attempt, so sometimes some of the intricate results, they were hidden. Alright, so these are all the possibilities. Alright, let me move it to the left hand side a little bit. Alright, So now if you look at the end result, that would be red, red, and red. Alright, let me finish the other result. So they come up magically like this. Alright, these are every line here is one possible event. Alright, from the results of the 3 dice. Alright, actually you should assign probability to each of these branches, right? But never mind this one, right? If you want exactly 2 red and 1 black, that would be 1 branch, 1 event, 1 event, 2 events, and 3 events, alright? These 3 blue ticks correspond to the 3 events that you have exactly 2 red and 1 black, alright? So it is repeated 3 times. Now how do that number 3 come from, alright? That number 3, either you did it like me, alright, you can do it like my way, that you do the manual counting, or you can imagine you have 3 dice, alright, and you want to pick 2 of them to be red. So the way to do that will be NCR will be 3C2, alright, 3C2 equals to 3. That's how we come up with the number 3 if you consider permutation, or in this case if you consider combination, alright. There are 3 dice and you want 2 of them to be red, alright. The ordering is not important. Whether it is first and second against second and first, they are the same, so it doesn't matter, right? So among 3 dice, you want to put 2 of them to be red. So the race to do that will be 3C2. Either you do the manual counting like here, or you do the NCR analysis like here. What important is, if you want to do it without the tree diagram, you have to think about this blue number. That is how the same branch is going to repeat itself. Alright, for most of the probability question, for the difficult probability question, that would be this blue number. Alright, try not to make mistakes like method number 1 or method number 2. Alright, these are wrong answers. Alright, only method number 3 will give you the right answer. And the difficulty in method number 3 is the blue number. Okay, if you draw the complete tree diagram, things can be clear, but it's spent too much time sometimes, alright? So let's take another example similar to this one to see whether you learn from it. Okay, or maybe we can do something like this. What if, now imagine, what if instead of 3 dice, I roll 4 dice? Alright, how likely is it to have exactly 2 red? Alright, we can have an extra bonus question here for you to think about, alright? If I roll 4 dice, what is the probability of having exactly 2 red, right? Roll 4 dice. What is the probability of exactly 2 red? Alright? Think about that. And you may want to pause the video and try this. The answer is, I'll tell you in 3 seconds, 2, 1. The answer is 8 out of 27. Alright? I'm not giving it away, alright? I want you to think about it. How come the answer is 8 out of 27? Think about it, alright? If you don't know, ask in the comments, alright? Or tell me so that I know you don't know. Alright. Okay, let's take a look at another similar example to this one. So it is like the railway, right? We have 5 screw heads in the construction parts. There's a 25% for each screw head to break. So the probability of breaking will be 1/4. Alright? The probability, on the other hand, for the good one will therefore be 3/4. Alright? So each screw head, either it is broken or it is good. Alright? If it is broken, then the probability is 1/4. The screw head has a 1/4 probability of being broken, and 3/4 to be good. Alright. So part A, we have 5 screw heads. Alright. Find the probability that all of them they are broken. So part A, all of them they are broken. 1, 2, 3, 4, 5. They are all broken. Alright. 5 of them they are broken. Now 5 of them, they are broken. There's only one way to do that, and that is 5 of them, they are broken. Alright, no combination, no permutation, because there's only one way to do that. 5 of them, they are all broken. So the probability will be just 1 over 4 multiplied to itself 4 times. Alright, that's 1 over 1024. Alright, but I want the answer to be as a percentage, so I do it on calc. 1 divided by 1024 times 100. The answer is 2 significant figure will be about 0.1%. 0.098, 0.1%, right? It's very unlikely to have all 5 screw heads all broken. Now, but part B is interesting. We want to find the probability that there are more broken than good ones, alright? More crosses than ticks. Find the probability that there are more broken screw heads than intact ones, alright? So, now let's decipher the meaning. What is the meaning of more broken than intact, alright? So either we have all 5 of them, they are broken, or we have 4 of them, they are broken, 1 of them is intact, alright? Or it is 3 of them broken, 2 of them intact, right? That's all, because the next one you will have more intact one than broken one, so this one is not counted. Or means we add them up together, of course, alright? It used to be or, but we know the calculation will be converted to addition, alright? These are mutually exclusive events. If you have 3 crosses and 2 tick, then it will not be 4 crosses and 1 tick. Alright, so that is mutually exclusive event. Mutually exclusive event, we add them together. Alright. So 5 crosses, we just did that, right? 1 over 4 to the 5th power. The branch only repeat itself 1 time. That is only 1 branch, alright? The branch with all the crosses. 4 crosses and 1 tick. The probability for each branch will be 1 over 4 to the 4th power, and then 3 over 4, right? This for the crosses, this for the ticks. But how many times this branch is going to repeat itself? Alright? Now you can do the manual counting, like, 4 crosses and 1 tick. It can be like this, right? That is 1 time. Or it can be like this. So that is the 2nd time, and then the 3rd time, and then the 4th time, and then the 5th time. There are 5 ways you can have this, alright? So it's multiplied to 5, alright? Or it is just 5C1, alright? There are 5 screw heads. You choose one of them to be good, alright? You choose one of them to be intact. There are 5 ways you can do that, alright? So that is 5C1, or you do the manual counting, it is 5, alright? And then the last challenge here is this one. We have, no, it's only 3, right? 3 of them, they are broken. So the probability is 1/4 to the 3rd power. 2 of them, they are intact. So the probability is 3 over 4 squared, alright? But what is the blue number you should multiply to here, alright? How many times this branch is going to repeat? 3 crosses and 2 tick, alright? You can do, once again, you can do it manually, like you can have 2 ticks and 3 crosses. Well, it is quite a lot of counting to do it here, alright? If you want to do it with counting. While I'm drawing the counting, you can use the NCR method. Try that. You can use the NCR method to see how many times this particular branch is going to repeat, alright? Well, let me see. Well, it's quite a lot of counting indeed, alright? And how about this one? I try not to repeat the possibilities, and also maybe this one, right? Oh, okay, I get the hang. This one, and finally this one, right? I counted 10, alright? This branch is going to repeat itself 10 times, 3 crosses and 2 tick, right? It can be, say, the 1st and the 2nd screw heads that are good, or it may be the 2nd and the 5th screw head that are good, and so on. Alright. Now, if you, for those who did it in NCR, what is this 10? This 10 is 5C2. Alright, and it is also 5C3. Alright. If you do it on the calculator, you discover that 5C2 is just the same as 5C3. By the way, this is also 5C4. Alright, for the 5 position, for the 5 screw heads, you pick 2 of them, they are intact. Alright, so that is 5C2. Anyways, it's multiplied to 10. Alright, so the final answer goes to, it is 53 over 512, right? So to 2 decimal places, it goes to 10%. Alright, there is a 10% chance they are more broken than intact ones. Alright, so this is how we do the tree diagram without drawing the tree diagram, right? You think about what are the branches you need, and most importantly on this page is how many times your branch is going to repeat, because you did not draw the tree diagram, right? So you can only imagine what would be like if you had drew the tree diagram. Alright, so pay particular attention to these blue numbers. Thank you.